let's start with our first example, and I'm going to do one that is relatively straightforward so that we are beginning with, something, I guess, easy-ish. Consider a book that is pressed up against the wall. You are pushing upwards on the book, like upwards and at an angle. So you have your palm against it and you're pushing it up the wall. And assume that the book travels up the wall with a constant speed. All right. I'm going to put numbers to this, but most of the stuff we will do in dealing with forces is going to be expressions. You're not going to have numbers associated with it, but we'll put a few numbers with this just so that we have, you guys who love to know if you got the right answer or not, well, you could have something there. We'll say that the book is 1.5 kilograms, and we're saying we're applying the force, let's go with an angle of 40 degrees and an applied force of 20 newtons. There we go. All right. So this is the first example of the day. So I'll step through the problem. But again, we're trying to do 4 today. So let's start with step 1. Is this going to be considered a first or a second law problem? First. Right, we know this is a first law problem. Net force is equal to 0. That is because constant speed. So once we see that, the fact that it's moving doesn't matter. The fact that it's moving at a constant speed, that matters. So handle that. Step 2, draw a free body diagram. A free body diagram reduces the mass of the object to a single point. Then all of the forces that are acting on the object are drawn as arrows started at the point and directed away. You have a list of forces that you should probably enact to this, but that's not an exhaustive list. There can be others that aren't on it, but it's to give you a place to start. So it's broken up into 2 categories, but there's really multiple subcategories in there. So we had fundamental forces versus contact forces, and then in contact forces, you have pulling forces, pushing forces, and resistive forces. So let's start with conservative forces, the fundamental forces. Are there any fundamental forces acting on this object? Hold on. Are there any fundamental forces acting on the object? Gravity. Yes, gravity. So we direct an arrow downwards. Here's where you are setting the scale for your drawing. This is this would be about 15 newtons long, right? The mass of the box is 1.5 kilograms. We've already talked about the fact that weight is mass times the acceleration of gravity. So that's 1.5 times 10. This is 15 newtons long. Now, I don't need a scale here. I just know that the force that I'm going to also put in here is 20 newtons. That one should be longer than this one. So as you're trying to establish your scale, make sure you have enough room to adequately handle the size of the arrows you're using, but also they should be relatively proportional to each other to represent the size of the forces that are acting. So let's go on. Is there any contact forces occurring to the object? Sure, we have several. Let's start with the first one. What do you think the first one is? Normal force is reasonable. It is pushed up against a surface. A normal force, by definition, must be perpendicular to the surface, which means this force must be directed to the right. Now, I'm not sure exactly how long to make this force, but I know that the book is moving upwards and the net force is 0. So I have kind of an expectation that my arrows are going to demonstrate balance. So however much force I have to the right, there should be the same amount of force to the left. But again, I don't have as much context here. I forgot to label these, so let's make sure we are labeling them as we go. I will use uppercase letters to signify forces when I can. Is there any other contact forces that we've missed? Friction is a resistive force, and I do think there's probably going to be a frictional force here. Drawing that one might be a little more complicated to us, so let's be careful here. What direction do we think friction would act in this case? Down is probably a good chance. If the book is sliding upwards, by definition, friction is a force that opposes motion. So if it's sliding upwards, this that suggests friction would be downwards. Now, I already have a force that's downwards. You have a choice on how you deal with the fact that there might be two forces in the same direction. The one that some people like is to stack the arrows like so. This is not generally what I do, but this is something you can do if you like. Stacking the arrows is just fine. I tend to prefer putting them side by side so all the forces are actually started from the origin. Neither is right or wrong. They're just different ways of doing the same thing. You choose what you want to do here. Are there any other forces acting on the object?
The force applied?
Yeah, there is a force that is given to us. I don't know what's causing that force. However, regardless of what's causing it, we have to use it the way it's been given to us, which means there is a 20 Newton force that is at an angle of 40 degrees with the horizontal. We must apply that force. However, you can't draw this as an arrow like that. For a free body diagram, all of the forces have to start from the object and be drawn away. So you must pass that force through and draw it this way. And then you must do some geometry to figure out how to deal with that 40-degree angle. Hopefully you guys have some skills already on how to do so. My experience has been that most of you know, but a few of you don't. So I will draw this to try and help you. Geometry, freshman year, these two angles are congruent because they are vertical angles. So based on that concept alone, this is where my 40 degrees is going to go and my 20 newtons there.
It's just the free body stuff.
What's that?
It's just, we include like the 20 newtons and everything on the free body.
Yes, since you have no other label for it. So we have completed a free body diagram and we've used everything we've been given and we've identified the reasonable forces that are likely acting in the system. Now, in order to actually make this useful, you need to apply a coordinate system because it's clear we have an off-axis force. However, if you are asked to submit a free body diagram, and tomorrow you will, this is what you submit for a free body diagram. You stop there. But if you have to do work with this information, draw a second diagram. This didn't take long to do, but draw a second diagram that can be used for you to actually do work. So that's what's going to happen next. I'm not going to draw a second diagram. I'm going to do work right here. But tomorrow, again, if I say I want a free body diagram or the problem asks for it, stop here. This is a free body diagram. Now, for us, we need to break up our off-axis forces into components. You can only do that when you've determined a coordinate system that works for your problem. I hope that we can all agree that the best coordinate system uses the second of the two priorities. Because this isn't accelerating, I don't have to force the direction to be in the direction of the acceleration. I can decide on one in which as many of the forces possible are lined up with my coordinate system. So I'm thinking something like that as a coordinate system. I'll identify this as the positive x direction. This is the positive y direction, and so on and so forth. Only one of my forces is off axis. Because of that, all I need to do is take that one force and break it up into components. Some of you, regardless of whether you've seen this once or 100 times, you have trouble with this, but you're just finding a triangle that works. But more importantly, that triangle needs to be aligned with your coordinate system, which means there has to be one component that is perfectly lined up with the x direction and is parallel to the x direction, and one component that is perfectly lined up with the y direction and is parallel to the y direction. So that suggests an arrow like this and an arrow like this. One that's aligned with the y direction and one that's aligned with the x direction. And once I've done that, this is 20 sine 40 degrees, and this one is 20 cosine 40 degrees. All okay? Now, once you have actually identified these components, we've added arrows to the free body diagram that actually aren't there. So the truth is, these two new forces, they take the place of the 20 Newton force that was there before. And this becomes your new free body diagram, the one that you're working from. Now, I'm not saying you have to redraw anything like that. I'm saying that they replace that force. These components completely define the same thing as the force that was there before. But now all of our forces are aligned with our coordinate system. So now we can apply Newton's law to our problem. Newton's law said that the net force equals 0, but now we say the net force in the x direction equals 0, and the net force in the y direction equals 0. And this becomes 20 sine 40. I'm sorry, not sine, x direction. 20 cosine 40 minus normal equals 0. I add up all the forces that are in the x direction and set them equal to 0. And then 20 sine 40 minus friction minus weight equal 0. I've added up all the forces that are in the y direction and set them equal to 0. That's what I want you to do tomorrow. That's what I'm expecting on your pop quiz. You will use all the series of steps to eventually get to this. That's tomorrow. The next day, I will make you go one step further. The Thursday, you'll go one step further. And by Friday, you'll be getting me answers. But this is what I want to see if you can do tomorrow. Does everybody understand? This is where you'll end. You'll get all the way through to step 3, applying Newton's laws and creating formulas that can or cannot be used to solve our problem. Yeah?
You said we'd have less than 10 minutes?
Less than 10 minutes. And yeah, I know that's a short amount of, but we're focused on doing the analysis today. So I'd like to present another example. You guys okay with that? All right. We're going to do a sign that's being held up by 2 ropes. So imagine a storefront or something and a sign, and there is a cable holding this part of the sign that is perfectly horizontal, and a cable holding this part of the sign that makes an angle of, let's go with 60 degrees with the horizontal. And let's say our sign has a mass of 20 kilograms. Typical kind of question is, what is the tension in the 2 cables? Okay? How about you guys do step 1 and 2? Can you just set up a free body diagram and decide whether this is a first and second law problem? I want you guys to start the problem, then I'll come in after a few seconds. Add the time you need. This is a net force equals 0 problem. The sign's going to stay there, static. I'll draw a dot to indicate the mass of the sign. Is the sign experiencing any fundamental forces? Yes, of course. So I'll draw a downward arrow to represent gravity acting on the sign. This arrow represents something that's about 200 units long. All right, 20 times 10. There's at least 2 forces causing tension. There's 2 cables connected to the sign. One of them I know has to be drawn so that it is perfectly horizontal. I don't really know how big to make this, so I'm going to just go with something that's reasonably sized. And now I know there's another cable. I'm going to try and anticipate 60 degrees, but I'm looking for balance. I want the up portion and the down portion to be about the same, left and right to be about the same. That's it. That's the free body diagram. It's not sliding, so it's not in contact with any surface, so there's no normal force. If there's no normal force, there can be no frictional force. It's not moving through a fluid, so I don't think there's any drag. That's the limit of what I have to apply. I need to have some labels, so I'll go W for weight and maybe TR for the tension on the right and TL for the tension on the left. But that's it when it comes to drawing a free body diagram. Now, there's more that I would expect you to do from here. You should draw a coordinate system, something that you can use to break this up into its regular component vectors. So I'm thinking a component that would work out best would be one that's aligned with the most number of vectors. This system's not accelerating. Something like so. I'll label positive y, positive x, negative y, negative x. I'll draw in what I do know. 60 degrees. That's it. Now I need to break this up into component vectors. So it looks like only one of them is off axis. This one. So I'm going to draw a triangle that I think will work best to break this up into its component vectors. And that's going to be a vector that's horizontal, aligned with the y direction and is parallel to the aligned with the x direction and parallel to the x direction. And one that is aligned with the y direction, parallel to the y direction. I'm going to do the trig right here in line with it all. This has to be t left sine 60. This has to be t left cosine 60. Once I've made those decisions, those can go away. These two new vectors define the original vector that was there. Now we've done most all the heavy lifting. It is true net force equals 0. So I'll do that in the x direction and I'll do that in the y direction. Now all you have to do is pick out the ones that are in the y direction and the ones that are in the x direction. Looks to me like TR minus TL cosine 60 equals 0. And TL sine 60 minus W equals 0. Again, this is how far I'm going to expect you to get tomorrow. Now, are you capable enough to find out what TL and TR actually are in this problem? Can you do the algebra? Prove it. I'm going to call on two of you. One to give me each one of those numbers. I want TL and TR. So increase your effective response. You're going to have to speak out loud, and somebody's going to tell me what TR equals, and somebody's going to tell me what TL equals. Yep. Kind of deal with here is, there's just a little bit of math here. Not a lot of math, by the way. Just a little bit of math. But I also want to show you something clear. If you actually did this, if you actually built this to hold the stupid sign, and you bought stuff that was able to hold the sign because it could hold 200 newtons, you understand you'd have a problem? Do you see what I'm saying? So if you weighed the sign and it weighed 200 newtons and you bought rope that could hold 200 newtons, it wouldn't be enough. By setting it up like this, unfortunately, one of them is overstressed compared to the other. That's why people build stuff all the time that doesn't work, especially when it comes to like kids and backyards. Parents go and build something, say, yeah, this rope will hold my kid. No, it probably won't, because you didn't anticipate what the kid was going to do or the fact that they might grow. All right. kid pulls on a wagon, applying 20 newtons of force at an angle of 30 degrees to a 15 kilogram wagon. The wagon accelerates to the right at half a meter per second squared. Can you figure out how much resistive force must be acting on the wagon? And how much normal force might be acting on the wagon? So again, kids pulling like 20 newtons, angle 30 degrees, wagon accelerates 0.5 meters per second squared. Can you figure out how much resistive force is acting on the wagon, how much normal force is acting on the wagon? Minutes left. I want to get at least one more of these in. Resistive force is about 10 newtons, and a normal force is about 140 newtons. know if you're doing it right or wrong. It's kind of our targets right there. Yeah. All right, so I don't know that there's friction acting in this problem. I want to be very clear. For those of you who use the lowercase f and indicated friction, look, it's not sliding, it's rolling. But I didn't ask for friction, I asked for any resistive force. Clearly, if you looked at the math here, the net force on the system is different than the unbalanced force on the system. And for those who don't know what I'm talking about, it's vocabulary. You have to be listening to the vocabulary. Let's take a look at what we have. Let's start with just drawing out our free body diagram. Is there a conservative force that acts on the object? Yeah, so I'll draw a downwards arrow to indicate gravity. I'm pretty sure this is the largest force that acts on the object. Is there a tension force that acts on the object, a pulling force? Yeah, I'd say that force from the handle would probably qualify. So I'll draw an arrow to indicate that. It is going to be clearly smaller, but at an angle of 30 degrees, something on that order. Is there a normal force acting on the object? Is it in contact with the surface? Most definitely. So my normal force must be perpendicular to the surface. That's going to be an upward force. And I'm purposely making it smaller than the weight because the tension force is also lifting upwards on the object. So weight, tension, normal. These are unbalanced, but it was suggested that there is a resistive force acting on the object. Resistive forces are going to somehow prevent it from moving or try to prevent it from moving. What makes the most sense on what direction to draw that? Left. So I'm going to draw a force to the left, smallish, because I know it has to look unbalanced. So I'm just going to say that this is some form of resistive force. I have to choose a coordinate system that best lines up with either the acceleration or the most number of forces. Well, unless the upward force was great enough to lift this thing off the ground, it's going to move along the ground. And since we were told it's accelerating, the best decision here, and these are all decisions you have to make. The problem isn't going to tell you this. If this force was great enough to lift it off the ground, then you would have to anticipate that. But I don't think the 20 newtons in any angle is going to lift off a 150 newton wagon. So I think we're okay to assume it's going to stay on the ground. So I'm going to make a coordinate system that is lined up with the direction of the acceleration. That will be this way, the positive x direction. And that will force the other coordinate system to be lined up in the y direction, like so. So positive y, negative x. I have one force that is off axis, so I'm going to have to break this force up into its components. There are two, of course. So I'll have a horizontal arrow here to indicate the force that's along the x direction, and a vertical one to indicate the amount of force that's in the y direction. T sine 30 and T cosine 30. Once I've done that, don't need this anymore. There we go. That's what we're left with. Now, we purposely set the x direction in the direction of the acceleration. And we lined up the x direction purely in the direction of the acceleration so that we could state there was no acceleration in the y direction. We are trying to create those conditions. Now that leaves me with T cosine 30 minus whatever the resistive force is equals MA. And I also get T sine 30 plus normal minus weight equals 0. Again, I'm expecting you to get here tomorrow. But you know things about this. You know the weight is mg. You know the tension is 20 newtons. And you know the mass is 13. I mean, you know things about this problem. Which means you could have plugged it in and found that the resistive force is about 10 newtons, like 9 point something, and the normal force is 140 newtons. That's the math part. I'm not particularly interested in the math part. All right. Questions?
Wait, can you explain how you know which one to set MA and which one to set?
You choose it. Guys,